Algebra 1, Lesson 13, and we'll look at Lesson 14. Lesson 13 is all about calculating and comparing square roots. So being able to say, what number is it near? Okay. We have some vocabulary terms in this lesson, like perfect square. That is a number that is the square of an integer. Basically saying maybe we have 2, an integer, and we are going to square it. Well, then 4 is going to be our perfect square. Or maybe we take 5 and square it. Our perfect square is 25. Even a negative integer like -3 means that 9 is a perfect square. Our radicand is the number or expression under a radical symbol. So if we have the square root of 36, well, that means that 36, that number, is the radicand. Square root, a number whose square is a number times itself. Okay? Basically what we are saying is, we all know that the square root of 36 is 6. Well, that's because 6 times 6 equals 36, a number times itself. Okay, let's continue on. So, if we look at some perfect squares, think about what are some of the first 15. Thinking of things like 25, 36, 49, 64, 81, 100, and so on. It's important to know these because as we take these square roots and simplify them down, being able to know those perfect squares is going to be very helpful. Our square root symbol looks like this, like we said. And if we look at the square root of 50, well, 50 is the radicand. 2 root 18, 18 is the radicand. Okay? And let's look at these. Well, if we take our numbers and show them in a chart like this, we can see that our perfect squares end up being in a diagonal like this. But what's also very interesting about this is their number or their name comes into play. These are perfect squares. So if we think about the number 9 right here, well, we know that's 3 times 3, which is exactly a 3 by 3 box. It makes a perfect square. Or 5 by 5, which is 25, a perfect square. 49 gives us 7 by 7. Literally, we have perfect squares with these numbers because we can make perfect squares with the side lengths, which is the square root of those numbers. Estimate the value of square root of 50 to the nearest integer. Well, this comes from looking at the square root of 50 and saying, all right, what are some perfect squares that are near 50? Well, we can think about it and say, how about the square root of 49? That's close to the square root of 50. And on the other side, the square root of 64. Those are the 2 nearest perfect squares under their radical symbols. And we can say, well, 49 is the same as 7. Square root of 64 is the same as 8. But which one is it nearest? And if we were to put these on a number line and say, which one is 50 closest to? We would see that 50 is closest to the square root of 49. So we would say it's closer to 7. Estimating that. Let's try this one. The area of a dance floor is in the shape of a square. Its area is 289 square feet. What is the side length of the dance floor? Well, this goes back to those perfect squares that we're talking about. If we were to continue that chart on and on and on and have a little box right here that says 289, well, what would be the side lengths to give us that? Would it be 14 times 14, 15 times 15, 16 times 16? No, it would be 17 by 17 because 289 is a perfect square. Okay, so we would say the side lengths of the dance floor are 17 by 17. Okay, let's talk about a couple of these. Is the radicand in the square root of 225 a perfect square? And we would know yes, because 15 times 15 is 225. How about root 350? Well, no whole number times itself is going to give us 350. So no, 350 is not a perfect square. Root 37. Well, if we look at the square roots that are near it, we would say it's near root 36 and root 49. And it's definitely closer to root 36, which is 6. Okay, compare the expressions square root of 16 plus square root of 441. Compare that to root 81 plus 361. Well, we have to think about what are these closest to. So, we can take some of the ones that we know, like the square root of 16 is 4. We know that. Square root of 81 is 9. And now we have to look at the square root of 441. Is that a perfect square? Well, we know it's going to be higher than 20 times 20. So maybe it's 21 times 21. And when we do that, 21 by 21, we get 1, 2, 2, 4. And we do, in fact, get 441, which means that that is 21. How about 361, the square root of 361? Well, it's going to have to be lower than 20 by 20, so how about 19 by 19? So we get 81, 9 and 8 is 17, and 9 and 1. So we get 1, 6, and 3, and we see the square root of 361 is 19. You can see how important it is to know our perfect squares. And we can see that 4 plus 21 is 25, so that expression is 25. 9 plus 19 is 28, which means that the first expression is less than the second expression. Lastly, the city park has a new sandbox in the shape of a square. The area is 169. What is the side length? If you know your perfect squares, you know that 169. If I take the square root so that I can find the side lengths, well, that means that we have 13. 13 feet by 13 feet is the side length of the sandbox. So just a little bit about our square roots there, and we're going to move on to probability, lesson 14. Theoretical probability of simple events. So first of all, some vocab. Sample space, we're talking about all of the possible outcomes. For simple events like a number cube, we could have 1 through 6. Those are what would come up on a number cube. A simple event is an event having only one outcome, so like rolling a 5 on a number cube. Theoretical probability, this is what we expect to happen if the world was perfect. This is the ratio of favorable outcomes to possible outcomes. So like rolling that 5 on a number cube, well, there are 6 possible outcomes, so we put that on the bottom of our ratio, and 5 can come up only once in those 6 options. So that probability would be 1/6. Okay, so if this probability of getting a 5 is 1/6, a complement to that would be the probability of not getting a 5. So if we have it down here, probability of getting a 5 plus the probability of getting not 5, those are going to add up to 1. And we see they do because this is 1/6. And if we don't want a 5, then we want a 1, 2, 3, 4, or 6, which is 5 out of the 6 outcomes. And that does equal 1. So a complement is the set of all outcomes in an experiment that are not in a given event. Another way to say this theoretical probability is what we think will happen. Number of successes divided by the number of possibilities. So if we look at some simple events like this, what's the theoretical probability of getting a 6? Well, that's 1 out of a possible 6. Probability of getting 7, well, we can't get a 7 on a number cube, so that would be 0 out of 6, or just 0. Probability of getting an even number, well, we're looking at 2, 4, or 6, so that's 3 out of our 6, which is 1/2. Let's see if, there we go. And probability of getting greater than 3, we're looking at 4, 5, and 6, so that's 1/2. Probability of less than 5, that's 1, 2, 3, or 4, so 4 out of 6, which is 2/3. These are simple probabilities, the theoretical probabilities. Now you know that in 6 rolls we may not get a 6, we might get a couple of other numbers, but if we continue to try and try, our probability would show that 1/6 of the time we will get a 6. Okay? Let's think about some other situations like this one. We have a bucket that has 10 balls numbered 1, 1, 2, 3, 4, 4, 4, 5, 6, 6. Single ball is chosen. What's the probability of drawing a number greater than 4? Well, if we want greater than 4, then we want a 5, 6, or a 6, which means that this is 3 out of 10. The question is, would you want to bet on that, or would you want to bet on getting the number 1 on a ball? And we can see with that we have 2 1s, which mean that we have 2 out of 10 possibility for that. I would bet on getting a number greater than a 4 because that has a higher probability. Here's some other examples that you can work on. We did a couple of these type. Okay, probability of randomly choosing a blue marble. Well, if we have 10 total marbles and 3 are blue, we would have 3 out of 10. Or randomly choosing a red marble, well, we still have 3 red marbles, and so we have 3 out of 10. Okay? I hope this was helpful for studying and for homework.